Hi, this is lesson number 12 on mechanisms. Just a review of the schedule. This is basically the end of our lessons for the second portion of the class on kinetics, looking at the speed of reactions. When this is posted May 1st, we will have Zoom office hours. Homework number 9 is due that night. Next week, we have homework all 3 days. With the 12th, homework number 12 being via Sapling next Friday. On Wednesday, there's a quiz, just similar to quiz number 1, again on Blackboard. And then the test will be on May 11th, and that'll cover lessons 7 through 12, right? So what we're finishing today. One other thing, there is a survey on Blackboard. It's on that left-hand side. Go ahead and look that up. It is due by Wednesday, May 6th. You don't have to do it. It's totally optional. It's totally anonymous, but it just lets me know what's working, what's not. Okay, the quiz 2, this is just some information similar to last time. Between 2:40 and 4 p.m. There'll be 2 to 4 problems. They'll be on rates and differential rate laws. That's lessons 7 and 8, and then integrated rate laws. If it is 4 problems, that means probably some of them will be multiple choice or something. Zoom on May 6th during the quiz. I won't have questions on the actual quiz, but I can answer any other questions, including homework. Okay, so let's do a little bit of a review on first order reactions. So for first order reactions, we said the half-life, remember that's the amount of time for half of whatever we're looking at to react, is equal to ln2 over k. Now this half here, remember this is a symbol, right? So you don't divide by 2 or anything like that. Okay, so if k equals 30 seconds, what is the half-life? Notice it's seconds to minus 1. So what we're going to do is we're going to just plug this in there. So ln2 is 0.693 divided by 30 seconds to minus 1. And I get 0.0231 seconds. What that means is if I start off with 2 molar of something, 0.02 seconds later, I'd have 1 molar of it. Okay, so that's very fast. Let's look at something in reverse. Let's say we're told the half-life and we want to know k. Well, what we have to do is we need to rearrange this equation. We can do that by getting k equals ln2 over half-life. And so then I just plug in my half-life here, 0.693 divided by 22.5 years. Notice that I have different units. So my half-life, or my rate here, is going to be 0.0308 years to the minus 1. Let's just look at these two half-lives, 22.5 years and 0.02131 seconds, right? The short lifetime here means that it's a very fast reaction. A very long life means it's a very slow reaction. All right, and notice we've only been dealing with first order reactions. Why don't we care about 0 and second order reactions? That's because they involve concentration. They're dependent on the concentration. This is not dependent on concentration. So it's something that's more useful. And in fact, we see this in nuclear decay. Okay, so let's move on and let's talk about reaction mechanisms. Now, we've already talked a lot of things about reactions like this, fire. We talked about the stoichiometry in 215. We talked about the heat involved. We talked about how to figure out delta G. This is all part of what we call thermodynamics. And then in the last 2 weeks, we've been talking about kinetics. That's the speed of the reaction, and that involves K. And then today we're going to talk about reaction mechanisms. That's how this reaction actually occurs. And so remember when we were talking about kinetics, we said, hey, typically, if I increase concentration, my reaction increases. And if I increase temperature, my reaction rate increases in speed. Why is this? It's because of reaction mechanism. Okay, so what is reaction mechanism? Reaction mechanism is the process by which a reaction occurs. Okay? So for instance, CO plus O2 going to CO2 and O, This is what happens in catalytic converters. How does this compound here, remember these are Lewis dot diagrams, in this compound right here, go about to form these? It's not just magic. What actually has to happen is a reaction has to occur. And reaction mechanism is the process by which this happens. All right, so what we're going to do is we're going to start off with something called collision theory. Collision theory tells how molecules must collide in order for a reaction to occur, right? If this CO molecule is in Toledo and this one is in, oops, that's the exact opposite of what I want to do. This one is in San Bernardino, they're not going to react. They need to be together and they need to actually collide. And the stupid analogy I kind of think of it is, how to do a high five, right? You can have a good high five where you both meet, or you can have a bad high five where everyone feels stupid afterwards, okay? All right, so what does collision theory say? There are 3 tenets to collision theory. The first is that the reaction rate is proportional to the number of collisions. That means the more collisions between CO and O2 that happen, the more likelihood there is going to be to have a reaction. And so this explains why as CO and O2 increase, the collisions increase, and therefore my rates increase. Okay? That's what we saw last time. And it's kind of like this stupid GIF at the bottom, right? If the girl in the black dress, if she's not going to high five, there's not going to be a high five, right? You need to actually collide hands for that high five to occur. All right, the second tenet of collision theory is that orientation matters. Okay? Now, in order for CO and O2 to form CO2, this right here is CO2. Okay? Notice it's an oxygen bonded to carbon, that carbon's bonded to another oxygen. So what that means is that this carbon is going to have to collide with the oxygen, right, in order for them to start bonding. What if the oxygen on the CO hits that oxygen? Well, now it's not going to form this compound here, right? Because now I'd have some kind of bond between the oxygens, and that's not forming this compound. So this would have no reaction, right? So it's not just that we have to have a collision, but they have to be in the right orientation, okay? What does this mean for a high five? There's always this awkward where someone goes for a high five and someone goes for the fist pound, and then it's like, what is this, right? So orientation matters. All right, the third rule of collision theory is that you need enough energy, okay? Notice this stupid thing, I think it's in London, where someone puts their hand up and someone else puts their hand up, but in order for a high five, you have to have energy, right? Just putting your hands together, that's not a high five, right? You need energy. Okay. All right, and that's the same thing for reactions. In order for this CO and this O2 to actually reorient itself, you need to have some energy, right? In order for, these are electrons that bond this. These are electrons to bond this. In order to do that, you need to have enough energy for those electrons to want to move, okay? And this explains why, as temperature increases, you have more energy, so you get more reactions. All right, now there's one other part of collision theory, and that is that we had our beginning molecules, our reactants. We have our final molecules, our products. And somewhere in between these, we have what we call a transition state. A transition state is somewhere between reactants and products. And you can look, it's kind of a blend between the two. So transition states are temporary arrangements between reactants and products. Okay? They have a very high potential energy, right? So this, right, is very high energy. And that's why this doesn't last very long. Instead, it goes and it forms this compound right here, because the universe likes low energy. So it has highest potential energy. That means it's very short-lived, right? Usually, we couldn't ever see this compound here, right? We can see these compounds here, and we can collect them in cylinders, etc., but we could never have this compound, this transition state. Sometimes it's called the activated complex, so if you ever see that, they're the same thing. Okay, this is kind of like, this is President Bush, this is President Obama, right? In between, right before President Obama took the oath, was this guy the president? That's what a transition state. It's somewhere between the two. This guy doesn't really exist, right? But it's kind of a blending between the two. All right, so let's go ahead and let's use something called a reaction progress diagram. Okay? The reaction progress diagram shows the energy as we go from reactants to products. So we're going to plot here energy on the y-axis. So high energy is up here, low energy is down here. And on the x-axis, I'm going to have the extent of the reaction. Okay, so this is the beginning, this is the end. Okay, this is the start. Okay, so what happens? I have my reactants right here, and I have my products here. The difference between these two, this is my delta H. So in this case, you can see that the energy goes from high energy to low energy. So it's losing energy. So this would be something we call exothermic. In this case, delta H is negative. All right, but between the reactants and the products, we have here that transition state. Sometimes we show it as, it's kind of a blend between A, B, and so we put a asterisk next to it. That just means this is high energy, okay? And this is the highest energy of them all. We already talked about this. The energy change during the reaction was H products minus H reactants, so it's this term right here. Okay. All right, so how does a reaction go from reactants to products? Well, it goes by going to the transition state and then down, right? So I'm in my reaction, I'm going from here to here. Okay. And so we have basically, between the reactants and the products, we have a hill, right? Or an energy barrier. This is what we call the activation energy. The energy difference between the reactants and the transition state, okay? And now, here's the thing. In order to go from reactants to products, what has to happen? It needs to have enough energy to get up this, to get to that transition state before it comes down, right? It's kind of like if I'm driving from somewhere and there's a mountain between, or actually, if I'm somewhere and there's a hill going down, I could go from A plus B to C plus D just by coasting, right? I could just turn off my car, undo the brake, put it in neutral, and it'll coast down, right? But if there's a hill in between us, right, what do I have to do? I need to turn it on, put on the gas to get over that hill. That's what transition states and activation energy are. Okay? Okay, so what happens is that collision that we said occurs, right, because we were talking about collision theory, that collision must have enough energy to get over that energy of activation, right? By the way, we signify activation energy as EA. Okay, so we can see here that on the plot, it's this term. All right, so from an a reaction progress graph or diagram, we can see and we can actually calculate the delta H and the EA. My delta H is always going to be products minus reactants. In this case, that'll be 2 minus 6 kilojoules. So that's going to end up giving me minus 4 kilojoules. And for my energy of activation, it'll be 12 minus 6. So it'll give positive 6 kilojoules. I think I talked about this later, but let me just state it now. Energy of activation, activation energy, will always be positive. Okay? The reason is that, remember, it's a barrier, right? It's a hill. If I had a negative energy of activation, it looks something like this, right? And this is no longer a barrier, right? So energy of activation will always be positive. Delta H could be negative or positive in the same way we were talking about with exo or endothermic. All right, so this is an exothermic reaction. We can also have an endothermic reaction. See, in this case, we would have a positive 4 kilojoules. And if I'm going from reactants to products, that would give me an energy of activation of 10 kilojoules, right? So my energy of activation always positive. Delta H can be negative or positive. Let's look at those two examples, right? So this is an exothermic reaction. This is an endothermic reaction. And these are basically the reverse of each other, okay? Notice how when I reverse the reaction, what happens? My delta H just changes sign. We already knew that because we knew that in thermodynamics. But what happens to my energy of activation? My energy of activation doesn't flip. And in fact, the relationship is dependent on this delta H, right? Okay, so let's do a problem. This is video problem 12A. And what I want you to do is figure out the delta H and the activation energy for this reaction here. So this is 125. This is 25 kilojoules. Okay. So figure out these two terms from that. Okay. Then what I want you to do is I want you to figure out delta H and EA for the reverse reaction. Hint, go ahead and redraw this diagram here for that reverse reaction. What's now my reactants? What's my product? And then you can figure out delta H and EA. Okay, so let's move on. And let's talk a little bit more about that activation energy, EA. Now, activation energy can be related to K, my rate constant, based on something called the Arrhenius equation. The Arrhenius equation is this, that K, the rate constant, is equal to capital A, E to the negative EA over RT, where A is a experimentally determined constant, and this is just what's called a frequency factor. It's the number of those collisions with the correct orientation, right? Because remember, we said that just because there's a collision doesn't mean it's going to form a reaction, right? You need to have Tiger Woods putting up the hand and his caddy putting up the hand instead of someone doing a fist pound, right? So you need to be careful with that. Okay. EA is our activation energy. It's in joules per mole. Now, notice what happens. And we'll do an example in a little bit. But as EA increases, this term is going to become more negative. So what does that mean? My K is going to decrease. This makes sense because if I have two reactions, One's like this, and the other's like this. This one has a smaller EA, and remember, this is a barrier between reactants and products, right? So that smaller EA is going to allow the reaction to occur faster, right? So small activation energy, fast reaction. Big activation energy, slow reaction. Okay, R is the ideal gas constant. It's in a little different terms. It's in 8.314 joules per mole K, right? Remember, when we're dealing with gases, we were using liters and atmospheres, but now we're dealing with energy, so it's in joules. All right, and then temperature is in Kelvin. And we'll do another example with this, but as T increases, okay, this term actually gets smaller, right? But it's negative, so it actually becomes a smaller negative. So that means K is going to increase, okay? And this makes sense because as temperature increases, there's more energy to get over that hill, right? Because remember, the energy is what does that. Okay, so what this means is if I want to increase the rate of a reaction, what can I do? I can either lower the energy of activation or I can increase the temperature. We know this second one because this makes sense, right? If I want to cook a turkey, which is just a bunch of reactions, I can cook it at 300 degrees C, it'll take so long. If I do it at 400 degrees C, it'll take half the time. If I do it at 1,000 degrees C, it'll burn within 10 minutes, right? So increasing the temperature increases. We'll talk more about this lowering activation energy in a little bit after we do some problems. Okay. All right, so let's do a problem. We'll do it at the board. So we're going to use that Arrhenius equation. K equals A, E to the negative EA over RT. And remember, I'm going to make sure to have my calculator nearby because using the exponents, that small e, that's going to be, I need to use my calculator for that. That I definitely can't do in my head. All right. So I have this equation. What am I told? I'm told an activation energy of 8.2 kilojoules per mole. I am told a frequency factor, that's that A, of 6.8. Let's see, molar to the negative 1, seconds to the negative 1. And then I want to know the rate constant at 25 degrees C. Okay, so I'm going to use this equation. The first thing I should do is I should make sure everything is in good units. Okay. Notice that R is in 8.314 joules per mole K. So seeing that I'm using R with joules per mole K, that means that I better have EA in joules, and I better have temperature in joules, okay? So I told you at the very beginning, you're going to get tired of converting from kilojoules to joules. Hopefully this becomes second nature. I know me saying that little spiel has become second nature to me. So I can convert 298.15 Kelvin. Okay. All right, so now I have everything in the right units. I can go ahead and I can use that equation. 6.8 molar to the negative 1, second to the minus 1 E to the negative 8,200 joules per mole. I don't know if you can hear it, but they're cutting the grass or the weeds outside or trimming, I think they are. They don't know we're in class, so forgive them. If they knew that we were learning about such fun stuff, they would stop and want to join in. That would probably break some rules. So, all right. Notice it's difficult. So if you want to do this and then plug it in, that's fine. So I'm going to get K equals 6.8 E. I'm going to do this term right here, 8,200 divided by 8.314 divided by 298.15. And this is going to get me negative 3.31. Notice joules cancel out, moles cancel out, Kelvin cancels out. So this is a unitless term. Okay. And remember that negative sign. If you don't use that negative sign, you're going to mess up. And this term here will always end up being negative because R is positive, T is always positive, and I just said EA is always positive, so it's going to be negative. Okay, so now, here's my value. I go ahead, I find my E to the X button, I go second, and then E to the X, your calculator may vary, and I get 27.3. So 6.8 times 27.3. Oops, wait, something's wrong. Did I just do what I said? I forgot to make it negative. All right, right? I forgot the negative. So when I do E, X, now I get a smaller number, 0.036, right? Okay. I told you. It's almost like I planned that, except I totally did not. All right, now I multiply by 6.8, and I get 0.249. Notice this doesn't have units, so I just have the same units as my A factor. Okay, so that is using Arrhenius equation to calculate activation energy. Or actually, using Arrhenius equation to use EA to find K. All right, so here it is on the screen. Now, I want to do one other thing. Okay? So we plugged everything in, made sure that negative's there, otherwise we mess up. And then I go ahead and what happened if instead of 25 degrees C, what happens if we want to do this at 100 degrees C? Okay? So I'm going to do everything the same except plug in this 373.15. Okay? What's going to happen is, and you can do the math, this will end up, this term will give me 2.64. Okay? Why? Because I increased temperature, and temperature's in the bottom, so that's going to get me a smaller number, but because it's negative, okay, I get a K from this of 0.48 molar to the negative 1 second. So what happened? I increased temperature, and my K increases. My reaction became faster, right? Remember, high K means it's faster, okay? Increased temperature, K increases. Okay, now let's go ahead and let's talk a little bit more about activation energy. And remember what we said, there are two ways to speed up a reaction. One is to increase temperature. The other way is to reduce energy of activation. And we can reduce the energy of activation by adding a catalyst. Okay? What do catalysts do? They bring down this activation energy. And bringing down that activation energy means the reaction goes faster. Okay? All right, so a catalyst is a compound that lowers the energy of activation without a permanent change. Okay? And what that means is that catalyst doesn't react away. I have the catalyst at the beginning, I have the catalyst at the end, right? I'm not losing it in the way, right? Now, we use catalysts a lot. We use it in catalytic converters on our car. They do it in a lot of industrial reactions. They're very important. Usually, a lot of times, they're metals. Okay? Catalytic converters use, I don't know if they use platinum or they use palladium, something like that. Okay, now some reactions will only occur with catalysts. Okay, some, you don't happen and then do it. Okay? All right, so what does catalyst do? Let's say we're going from A to B. We have this reaction here. This will be uncatalyzed. Well, what happens is having a catalyst lowers that activation energy, right? And that just allows it. Now, notice if I go from A to B or from B to A, in both ways, my activation energy is lower, okay? And so what catalysts do is they change the mechanism, right? How I get from A to B is now different, right? I may go through some other intermediate C or something like that. Okay, so let's get some just terminology. Now, we can call catalysts either homogeneous or heterogeneous. Homogeneous means that all of the compounds involved, the reactants and the catalyst, are all in the same phase. Okay? So that means they can all be gas, or they could all be liquid or aqueous. Okay? But usually gas. Heterogeneous, remember this was day 1 of 215, we learned about heterogeneous. Heterogeneous means different, right? So in this case, it's where the catalyst is in a different phase, right? So that means some things are gas, and then the catalyst may be a solid. Okay, one example of homogeneous catalysts is actually what happens at 40,000 feet above us in something called the ozone layer. Okay, now ozone, O3, is an awesome compound. Okay, it removes UV light. Okay, so what we have is at 40,000 feet above us, there's a bunch of ozone in the atmosphere. And what that does is that removes UV light by these two reactions, right? The ozone goes to form O2, and then that O2, and it produces an O, which goes ahead and reacts with another O3 to form O2, right? This is the mechanism by which we form this. Okay? And so what happens is that ozone gets converted into O2. Okay, this is a good thing. Okay, by the way, ozone is good here. It's bad at low altitude where we are, because at low altitude, that's where we breathe it. Okay, it's good up high, bad down low. Now, what happened is that we ended up having, as humans, we started producing a lot of things that produce chlorine. And these chlorine went ahead and they destroyed the ozone by a second reaction, right? And so what happened is the chlorine would be produced, would destroy the ozone, and then it would come back up, right? So it would be destroyed in one, and then it would be remade. And that is what's called a catalyst, right? But notice that these are all gases, and that's why this is a homogeneous catalyst, okay? By the way, there was a Nobel Prize in 1995 to two professors from UC Irvine who basically postulated this. And because of this, that work, we stopped producing things called CFCs, right? CFCs used to be in a bunch of, hairspray and everything. We got rid of these, and now we're protecting our ozone layer. Okay, that's a homogeneous catalyst, everything in the same phase. We also have heterogeneous catalysts. Heterogeneous catalysts are when we have things in different phases. Okay, for instance, catalytic converters, which I mentioned a few times, they remove pollutants from our car exhaust. Right. One of these pollutants is CO, right? CO is bad because when we breathe it in, it bonds to our red blood cells, which means they can't bond to O2, and we need O2 for life, all right, to live. Okay, so what catalytic converters do is they take that CO and they react it with O2. But what happens is this reaction only occurs on platinum, right? The CO binds to the platinum down here, the O2 binds to it, and then a reaction occurs to produce CO2, which isn't as harmful, okay? So this is an example of a heterogeneous catalyst because the catalyst here is a different phase, okay? All right, there's one other term we should know for catalysts, and that is something called enzymes. Enzymes are biological catalysts. These are what we call macromolecules. It's thousands and thousands of atoms, right? So when we think of platinum, that's one atom. O2 is 2 atoms. CO2 is 3 atoms. Well, if I have 1,000 atoms, I can get into something like a enzyme, right? And in fact, they become so big that you have to worry about their folding and things like this. This is all that what you learn in biology and in biochemistry. All right, but what do these enzymes do? They basically take a reaction, right, and they change the way that we get there, right? So they go ahead and they lower that activation energy, right? You can see here they actually change it by, you end up with 3 transition states instead of 1. All right, you don't need to know this one, obviously. This is too advanced, but this is actually something I stole from another professor of biochemistry. And so enzymes are very important when you talk about biology and biochemistry. Okay, so that's catalysts. Now let's look at that reaction I talked about earlier, the 2CO plus O2 going to 2CO2. Like I mentioned, this doesn't happen in one step, right? In reality, it occurs over multiple steps, right? We go from CO plus O2, that forms CO2 and O. And then that CO and O forms CO2. Right? And so what happens is catalysts end up changing the mechanism, right? They change how we go from reactants to products. Okay? So we get a different path and therefore a different transition. What catalysts don't do is they don't change the products and reactants, right? Notice the products and the reactants are in the same place here, right? They just change how we get there. Okay, so let's look at this in a little more detail, and let's talk about that reaction mechanism, right? So the reaction mechanism is the process by which the reaction occurs, right? And each step in that reaction we can call an elementary reaction, okay? And the thing is that with elementary reactions, they occur exactly as written, right? So in this case, a CO and O2 actually collide in order for there to be a reaction. Here, a CO and an O atom actually collide, okay? Now let's look at this reaction mechanism. So we take CO and O2, this forms CO2 and O. Now this oxygen atom reacts with another CO to form CO2. Okay? So this oxygen atom is made in one step, and then it goes away in the next. This is what we call an intermediate. Okay? They are ones that are made in one and gone away. So they don't end up showing up in the overall reaction, right? The overall reaction is what happens when I sum up all these reactions, right? The oxygen is going to go away because it doesn't, it's made in one, gone in the other, right? So intermediates are temporary, right, products. Okay, let's look at those elementary reactions one more time, right? So elementary reactions are each step in the process, okay? And they occur exactly as written, okay? Now, for reaction mechanisms, we can say something special. The rate law can be determined from the stoichiometry. This is different than what we've learned for everything else, right? For elementary reactions, if I look at that reaction, I know the rate law. Okay, so we can talk about elementary reactions as being unimolecular. That means we have one reactant, okay? For instance, A going to B, right? This happens a lot when we have something called decomposition. We take one reactant and it forms a transition state, and then it forms products, okay? Okay, so the rate law for a unimolecular reaction would just be rate equals Ka, right? Because there'd be a 1 here, but that doesn't occur. Okay. We also have bimolecular reactions. Bimolecular reactions have two reactants. These can either be 2A going to C or A plus B going to C, right? Two reactants, okay? And so, in this case, the rate would be either Ka squared or Ka times B, right? Depending on which reaction we're looking at. So if I look at that catalytic converter reaction I talked about, we have rate equals KCO times O2. And then for the second one, rate equals KCO times O. All right, so that's unimolecular. Bimolecular, we can also have termolecular. These have three reactants. Three reactants or termolecular reactions are very rare, okay? Why? Because you need to have three reactions occurring at the same, or three molecules colliding simultaneously. That's very rare. It'd be like a three-person high five. That really doesn't happen, okay? But if we had a termolecular reaction, it'd be rate equals KNO squared, in this case, times O2. This is only possible to do this because they are elementary reactions. Okay, so now let's go ahead and let's talk about some reaction mechanisms. Okay? All right, so let's say we have this reaction here. NO2 plus CO going to CO2 and NO. Okay? This reaction doesn't occur like this. It actually occurs in two steps. First, 2NO2 form NO3 and NO, and then that NO3 reacts with CO to form NO2 and CO2. Okay? All right, we can go ahead and we can sum up these two reactions the same way we did it with Hess's law. So I'd have 2NO2 plus NO3 plus CO goes to form NO3 plus NO plus NO2 plus CO2. Notice how this is very long and we have some redundancy. So we can actually get rid of this, and then we can get rid of this one and this, right? And we have this reaction here, okay? Notice that NO3 is not in the overall reaction, right here. That's because NO3 is formed in one step and then goes away. NO3 is an intermediate, okay? It's kind of like cooking. You know, I take some flour, I take some eggs, I take some chocolate chips, blah, blah, blah. I make some batter, and then I make cookies, right? That batter, that cookie dough, that cookie dough, that's an intermediate, okay? That's not my final product. I need to make that in order to get to products, right? So in this case, NO3 is an intermediate because we formed it in one step and then it goes away. Okay, so if this is the overall reaction, and these are the two elementary reactions, we could go ahead and we could write rates for each of these elementary reactions. So for instance, this one would be rate equals K times NO2 squared. This one would be rate equals K NO3 times CO. Now, these Ks aren't necessarily the same. That's why I call one K1 and one K2. Now, let's say I wanted to know the overall rate of this reaction. Well, can I figure out the overall rate? In most cases, I need experiments. But there is the possibility that one of these reactions is slower. If one step is slower, we call that what's called a rate limiting step. Okay? It's the slowest step in the process, right? To go back to my cookie analogy, right? I take those eggs, that flour, all that, I make the dough, I make the cookies, right? That takes a long time. Me eating the cookies, that's very fast, right? So the rate limiting step is the slowest step. Okay? So let's say we had that reaction that we talked about, and we said this first step is slow, the second step is fast. If the first step is slowest, it determines the overall rate, right? So this is slow, and then as soon as I form that NO3, it reacts, right? So if K1 is much smaller than K2, the overall rate of this is going to just be the rate of this first step, right? So overall rate equals K1 NO2 squared. Okay? All right, so I'm going to try to show a video. Let's see if it works. Okay, we're actually not going to play that video, but you can if you want. The link's right there. But basically what they did was they basically analogized the reaction as basically, let's say we had some cars going from point A to B to C. If there's no toll, nothing blocking them, they just go at their own speed, right? But let's say all of a sudden we put a toll booth here. And it's a toll booth that actually people have to stop and pay, right? Now, what's going to happen is the time going from A to B is going to be much slower than to go from B to C, right? So it'll take a long time to get from A to B, and then it'll be really quick. So this step right here, right, this is my rate limiting step, right? So if it's this first step, right, I can say, hey, the overall time is determined based on this first step, okay? Now, if the second step is slowest, right, like in this case where this is slow, it becomes more difficult, right? And additionally, if the two are about the same speed, etc. The reason why is if the second step is a slow step, I would have overall rate equals K2 NO3 times CO. But notice CO, right, or actually NO3. NO3 is an intermediate, so it can't be in here. So it actually becomes more complicated. So we're not going to worry about that. We're only going to worry about it is if the first step is the slowest. Okay. Now, reversible steps can also make it hard. And we'll deal with that next time when we have equilibrium. Okay, so why don't you look at video problem 12b, right? This is where we're going to go ahead and look at a reaction mechanism that has two steps, okay? Go ahead, take these two steps, these two elementary reactions, sum them up to get the overall reaction, determine what the intermediate is, figure out the rate laws for each of these elementary reactions. What's the overall rate law, because this first one's slow, and then what the rate limiting step is. All right, so go through that, and yep. All right, so that is activation energy. Activation energy, remember, is this barrier here between reactants and products. And we have this transition state. Remember, the key thing with transition states is they are temporary, okay? Now, the bigger that this EA is, the slower the reaction is. So we can do one of two things. We can either lower this, or we can provide more temperature to get past it, right? So to increase reaction rate, we either increase temperature, or we add a catalyst. Okay? Catalysts lower the EA by changing the mechanisms. We talked about homogeneous, heterogeneous, and enzymes. And then in mechanisms, we talked about unit, bi, and intermolecular, and rate limiting steps, which are the slowest steps, right? And we went through and we looked at what happens if that slowest step is the first. All right, so this was a long lesson. It kind of went through a bunch of different topics, and it was actually 3 different sections of the book, right? So make sure you study it, come to office hours if you have questions, and then homework is due on May 8th. All right, talk to you later.